Hi guys, so today what we're going to do is we're going to talk about how to convert from decimal numbers or regular numbers that you know, like this, to binary numbers, which are just made up of ones and zeros. We're going to go over why we do this, how we do this, and then do some iGCSE exercises. So let's get started. Okay, so why do we use binary? So when we talk to each other, we use our voice to communicate, and we use languages like English, Spanish, whatever, to communicate with each other. However, the language that a computer and all computer systems use is binary, so ones and zeros. So whenever we write code in Python, so for example, you might write a equals 23, print a. This just gets converted into a series of ones and zeros that's then run by the computer's processor. So basically, anytime we do anything in the computer, our actions and what we use in software is being converted to binary, which is then sent to the processor and is used to initiate all kinds of actions. The other thing that I want to point out, because of the fact that we're talking about how computers work, is that each digit in a binary number is called a bit. Now, this doesn't really make any sense until we consider what a bit is in the larger context of computers. So let's say we have an 8-bit binary number. So we have a binary number of 8 digits, like this. This means that this is an 8-bit value, each one of these being bits. Now 8 bits equals 1 byte. 1,224 bytes equals 1 kilobyte. 1,024 kilobytes equals 1 megabyte. And 1,224 megabytes equals 1 gigabyte. So looking at this, you can kind of see how binary numbers and how binary instructions have some kind of relevancy to what you know about computers. I'm sure you've all heard about a movie being 2 gigabytes, or you've downloaded a song that's 10 megabytes. What that really is just a series of binary numbers. Just a series of ones and zeros. And when you're talking about 1 megabyte or 1 kilobyte or 1 gigabyte, you're just referring to how many ones and zeros that particular file is made up of. Keep in mind those ones and zeros are then being interpreted in the computer to display your video or your music or whatever it is, or your text file or whatever it is that you're making use of. So knowing that, at this point, okay, you know that binary is just a bunch of ones and zeros. Let's move on to what that actually means in the context of mathematics and how we can convert a value we know to a binary value. So let's say we have the number, well, let's just start with regular numbers actually, right? Numbers we use every day are like 543, 1024, 21. You recognize these numbers. These numbers are called base 10 numbers. So base 10 numbers basically mean that we use 10 to the power of something to denote or show every single space. So for example, right here with 21, this is really 10 to the power of 0 and then 10 to the power of 1. Okay? And then to get 21, we're taking this digit right here. We're saying 2 times 10 to the power of 1 plus we're taking this digit right here, and then 1 times 10 to the power of 0. So it's giving us 20 plus 1 equals 21. Similarly, right here, we've got 543, okay? So we're going to go even further. We're going to say 10 to the power of 0, 10 to the power of 1, and 10 to the power of 2. And let's just move our calculation right over here. We're going to do 5 times 10 to the power of 2 plus 4 times 10 to the power of 1 plus 3 times 10 to the power of 0. We'll just put that in right here. That's going to give us 500 plus 40 plus 3 equals 543. And just to kind of like solidify this whole concept, I'm going to go to an even bigger number. All right, 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and then 10 to the power of 3. So keep in mind, each of these places stands for an increasing exponent to 10, because these are base 10 numbers. Base 10 with an exponent. So right here, we're going to have 1 times 10 to the power of 3 plus 0 times 10 to the power of 2, which is going to be nothing, plus 2 times 10 to the power of 1 plus 4 times 10 to the power of 0. And that's going to end up being 1,000 plus 0 plus 20 plus 4. Hence, we get 1,024. Okay, so this is kind of how this whole base system works and just how numbers work in general. So now that we have a pretty good idea of how our own number system works, let's go and look at how not a base 10, but a base 2 number system works. So just to rewrite this right here, we had 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and 10 to the power of 3. So what I want to do now is I want to talk about how base 2 numbers work. That's just getting cut off right here. It's my weird 8, isn't it? So base 10. So let's talk about how base 2 works. All right. Let's say we have a number that is like a binary number, which is base 2, 1, 0, 1, 1. Okay. We're going to do the same thing we did here, except we're going to use base 2 with exponents. So instead of 10 to the power of 0, we're going to have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. All right? And we're going to do the exact same thing we did here. We're going to do 2 to the power of 3 times 1 plus 2 to the power of 2 times 0, so just nothing, plus 1 times 2 to the power of 1. I kind of messed up the order there. Plus 2 to the power of 0 times 1. Okay? And we're going to add all of that up, and that's going to be 8 plus 4 plus 2 plus, oh wait, this was 0, so actually, let me just erase this right here. My bad. It's going to be 8. It's going to be 8 plus 0 plus 2 right here, and then plus 2 again, or plus 1. So 2 to the power of 0 is 1 times 1. So that's going to end up being 11. 8 plus 0 plus 2 plus 1 equals 11. Let's go ahead and let's try another example. Let's try a longer example. Let's say we have 1, 0, 1, 1, 1. Okay? 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. Kind of to make it easier on ourselves, we can even just say 1, 2, 4, 8, and then 16. Okay? So we can look at what we have here. We have 1, 0, 1, 1, 1. So that means that immediately we can just kind of get rid of this one right here. And we're just going to add up these. That's going to be 20 plus 2 plus 1, which is going to equal 23. And we'll go to an even bigger example, right? And I'll kind of illustrate something a little bit different right here. Let's say we have 1, 0, 0, 1, 1, 1. And then we've got some zeros right here. So again, the reason we're writing it in this format is to show you what an 8-bit binary value looks like, okay? Now these are zeros right here, so in reality, these aren't going to do anything for us. These are just end up being 0. But it's still kind of worth showing you this format just so you kind of see how it would appear in an exam situation. Or really in a computer context, because values like 8 bits, 16 bits, these are all kind of common values that are used in computerized operations. So let's go ahead and just kind of do this a long way. 2, 1, 2, 2, 2, 3, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7. Okay, and we'll write out these numbers just so you get an idea, or just so you get used to the type of values you'll be working with. 2, 4, 8, 16, 32, 64, 128. Okay. So these two right here are 0. So we can immediately just kind of get rid of these. These don't matter to us. This is 1, so we're going to need this one. This is 0, so we can get rid of this. This is 0, so we can get rid of this. These are 1, so we're going to need these. So ultimately we end up with 32 plus 4 plus 2 plus 1 equals, okay, we've got 36 plus 3 equals 39. Okay, so I hope that was kind of clear to you as to how we go from binary to decimal numbers or regular numbers. What we want to do now is we want to go from regular numbers that we know, decimal numbers, to binary numbers. So let's kind of just do a few examples in this context right here. Let's say we've got a number like, let's just do something simple, 9. Okay? So remember, we're talking about base 2 numbers, and we're going to have a series of digits like that are going to correspond to 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, etc. Okay? And this is going to be 2. Sorry, this is going to be 1. That one always throws me off. This is going to be 1. This is going to be 2. This is going to be 4. This is going to be 8. Okay? And then we have 2 to the power of 4, which is going to be 16, which we're not really going to use, but I'll explain why. So we've got this number 9 right here, okay? So basically what we want to do is we want to basically fit these numbers into 9. So we want to create a set of values that's equivalent to 9, okay? So let me just go through an example and I'll kind of explain how that concept works. So first, we want to look for the biggest one of these numbers that we can fit into 9. So 16 is too big, but 8 fits into 9. So we're going to put 1 right here, okay? So that means that out of 9, we've accounted for, or we have 8, okay? So now we only need to worry about 1. 9 minus 8, this 8 corresponding to this one right here, equals 1. So we can just do this right here. And then these can be zeros. So 9 is going to be equal to 1, 0, 0, 1. So the idea is about using these binary values right here to fill up 9, or to add up to 9. So to kind of illustrate that, I'm just going to do like a couple of examples, because this one is a little bit more difficult to wrap your head around than converting from binary to denary. So let's think about a bigger number, okay? Let's talk about 41. So we'll just write out our, well, actually, you know what we can even do is, well, let's stick with the exponents, and then we can, just for ease, or just for showing how this works, we'll write out the numbers again. 2 to the 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. Okay? It's going to come out to 1, 2, 4, 8, 16, 32, and 64. Okay? So out of these, let's think about the biggest number that can fit into 41. And 64 is too big because it's bigger than 41. So the biggest number out of all of these that we have here that we can fit in is 32. So that's where we're going to start. And we're going to put a 1 right there. Okay? So out of 41, we've accounted for 32. So we're going to do 41 minus 32. That 32 is corresponding to this right here. Okay, 41 minus 32 is equal to 9. So now we have 9 left that we need to account for in the remaining binary digits that we have access to. So now we just need to worry about 9 because we've already gotten 32 out of 41. So let's think about in this group right here. What is the biggest number that fits into 9? And 16 is too big, so we're going to put a 0 right there. But 8 is good enough, so we're going to put a 1 right there. Okay. And now that we've done this, let's do 9 minus 8. Okay, 8 corresponding to this value. That equals 1. So that means now, in our binary values, we only need to account for 1 more. Okay, and the only number that will fit into 1 is this one right here. So these two become zeros. So 41 equals 1, 0, 1, 0, 0, 1. Okay, so this arrow actually should have gone right here. My bad. So really, like, what we're trying to do is we're trying to take our binary values right here, and we're trying to fit them into 41. Let's do yet another example. Let's say we have 79. Okay, it's a bigger number. All right, so we're just going to go ahead and do our thing. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7. That should be good enough. So we've got 1, 2, 4, 8, 16, 32, 64, 128. Now, right here, what's the biggest number that can fit into 71? That's going to be 64. So we're going to put a 1 right here, okay? And like we did before, we're going to use 79 minus 64 because we've already gotten this 64 out of the way. So we'll subtract these, and now we have 15. So now we need to fill in this 15, all right? We need to account for this 15 using these remaining values right here. We started right here on this side. Now we need to use what's remaining inside, what's remaining after this, in order to account for this 15. Now 32 is bigger than 15, so we can't use this. 16 is also bigger than 15, so we can't use this. But 8 will fit into 15, so we can use this. So now we're going to do 15 minus 8 equals 7. And now we need to use these remaining digits to fill in 7. And 4 can fit into 7, so we're going to do this. 7 minus 4 equals 3. 2 fits into 3, which is remaining, so we can do this. 3 minus 2 equals 1, equals 1. And now we just got 1, so we can do this. So we're going to have 1, 0, 0, 1, 1, 1, 1. So that was a bit more of a complicated example. Basically what we're doing is we're starting with the biggest number. We started with the biggest number that could fit into 79. All right. And we started with that. And then once we found that number, which was a 64, we subtracted from 69. And then we focused on the next number. Okay. And then using these remaining values right here, we tried to add up to 15. And then we moved down, we moved in this direction until we pretty much got a bunch of binary numbers that would add up to 79. Okay. Let's just do one last example, and then we'll move on. Okay, so last example is going to be just kind of an average number. Well, not an average in the mathematical sense, but just a regular number. Let's say 54. All right. So with 54, we're going to look for binary digits that add up to 54. So we're going to do our thing, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7. Okay? It's going to be 1, 2, 4, 8, 16, 32, 64, and we can kind of stop there because 64 is already bigger than 54. 32 is the biggest number here that will fit into 54. So we're going to put a 1 right there. Okay? So now, because we put a 1 right here, we're going to subtract 32. And that's going to be equal to, what's it going to be equal to? Okay, 22. Okay? So we started right here. So now the number we're focusing on is 22. And we can see from these numbers right here, what is the biggest number that will fit into 22? And that's going to be 16. So we can just put a 1 right here, okay? And because we put this 1 right here, we're going to do 22 minus 16, which is just going to be equal to, 6, all right? So now we're going to look at these numbers right here. 8 is too big for 6, but 4 fits in. So we're going to put a 0 right here, and then we're going to move in this direction, we're going to put a 1, okay? So now we're going to do 6 minus 4 equals 2. Now we've only got 2 left, and so we can just put a 1 right here to account for the 2. And we can put a 0 right here, because 2 minus 2 equals 0, so we're pretty much done. So that means that 54 is going to be equal to 1, 1, 0, 1, 1, 0. So that's how you convert from denary to, or that's how you convert from denary to binary. Basically, you're starting out with your binary number, with your denary number, so 54 right here, and you're looking for the biggest number in this group of numbers that will fit into 54. And then you're subtracting that number from 54, and you just keep moving in this direction until you've reached 0, until you've basically filled up 54, or you have a set of binary digits that add up to 54. So I hope this was useful. Now that we've done this, let's go ahead and let's see if we can try to work with a actual iGCSE exercise. Okay, here what we're going to do is we're going to solve a typical iGCSE question, which is taking what we know about binary conversion and kind of using it in a more practical context. Okay, so right here we have a stopwatch. A stopwatch is basically like a mini computer, and it uses 6 digits to display hours, minutes, and seconds. Now, basically what's happening is this is what our stopwatch looks like. And the stopwatch itself, since it's a computer, is using some sort of binary internally to represent these numbers on the face of the stopwatch. So this is what's shown on the stopwatch, these decimal numbers. But really, they need to be represented as binary inside the stopwatch. So an 8-bit register is used to store each pair of digits. Now, a register is just a place to store data. It's kind of like a USB drive or a hard drive, but much smaller. It only consists of 8 bits, which means 8 binary digits. So we need to take our hours right here and convert it to binary, our minutes, convert it to 8-bit binary, and seconds, and convert it to 8-bit binary. So what we're going to do is we're going to get started. So right here, what we can do is we can kind of do something like this. We know hours is a pretty small number, so it's only 2, so we don't need to go too crazy. We can just say, it's really just going to be this one, right? Just 1. 2 to the power of 1 is 2. That's the biggest number that can fit into 2. And then the rest are just going to be zeros. What it is important that we fill all these in because it's asking us for an 8-bit binary number. So the next one is going to be minutes, which is going to be 31. That one's going to be a little bit more complicated. Let's go ahead and let's do that. So 2, 1, 2, 2, 2, 3, and 2, 4. And then 2, 5. So 2, 5 is 32, which is too big for 31. But 2, 4, 2 to the power of 4 is 16, which is just fine. So you can put a 1 right there, and then we can do 31 minus 16 equals 15. Okay. 2 to the power of 3 is 8, which fits perfectly fine into 15. So you can put a 1 right there. And then 15 minus 8 equals 7. And okay, so we can definitely just do 2 to the power of 2. 7 minus 4 equals 3. So we've only got 3 left. So, okay, we can do that. 3 minus 2 equals 1. And then we can just do that to account for 1. So that's just going to be this right here. Then we've got seconds, which is 58. It's kind of just, or let's clean some of this up right here. We'll just kind of erase some of this. So you have some space to work here. And let's convert 58. Okay, so 58 is going to be a bit bigger. We can go ahead and just write down our base 2's right here. And so 2 to the power of 5 is going to be 32, and 2 to the power of 6 is going to be 64. Just still going to be too big. So we're going to have to start with 2 to the power of 5, which is 32. So we're going to put a 1 right there, and we're going to do 58 minus 32 equals, it's going to be about 26. All right. So then we're going to go to 2 to the power of 4, which can fit into 26. So we're going to put a 1 right there, and we're going to do 26 minus 16 equals 10. Then we'll go to 2 to the power of 3, which is 8, which can fit into 10, so we'll put a 1 right there. We'll do 10 minus 8 equals 2. And we've got 2 to the power of 4, which is too big for 2. But we do have 2 to the power of 1, which is 2, which fits perfectly, so we can put a 1 right there. And these can end up just being zeros, because we didn't need these, or we couldn't use these. And to fill out our 8 bits, we're going to have something like this. Okay, so that's kind of how that works. Let's go ahead and let's just do another example now. Okay. So again, we've got another microprocessor alarm clock example. Well, actually, I guess the last one's a stopwatch, but we have something else involving time, right? And so it uses the 24-hour clock right here. The hour is represented by an 8-bit register A, which is this one. The number of minutes is represented by another 8-bit register B. So these are both storage space, and each of them is used to represent a particular aspect of the time. This one right here is used to represent hours, and this one here is used to represent minutes. And this is how they would be stored inside the alarm clock, in the microprocessor. They're going to be stored in binary because binary is what is used for all processes within a computer. But if we want to display them to a human being, they need to be displayed in decimal or denary digits. So let's go ahead and let's do that. They made it really easy right here, right? So we've got 0 for 128, 0 for 64, 0 for 32, and 1 for 16. 0 for 8, 0 for 4, and then 1 for 2. So we can just do 16 plus 2, which is 18. And then for minutes, we can do the same thing, right? So we've got 0 for 128, 0 for 64, and 1 for 32. We've got 1 for 16. We've got 0 for 8, so we just don't do anything with that. We've got 1 for 4, and then we've got 1 for 1. So we're going to add this all up. We're going to get 48 plus 4 is 52, plus 1 is 53. Let me just make sure I added that up right. Yeah, okay, so 30, did I? Okay, I think I made a mistake right there. Let me just go ahead and erase that real quick. Okay, so 32 plus, maybe I didn't make a mistake. Sometimes it's kind of confusing to do mental math. 32 plus 16 is actually 48, plus 4 is 52, plus 1 is 53. So we've got 1853, or on a 12-hour clock, 6:53 in the evening. So actually this one is super simple. Let's go ahead and do an example where we need to actually convert from denary to binary, which is honestly the more difficult of the two operations. So alarm clock has been set for 0730. Again, two 8-bit registers or two 8-bit storage spaces are used, C and D. And they represent the hours and the minutes. So 7 is going to be represented by this one, and 30 is going to be represented by this one. So we need to figure out the binary representations of these two. And for this one, since we've already kind of seen them just represented as regular numbers right here, I'm going to kind of dispense with that, and I'm just going to kind of copy what they did. So 1, 2, 4, 8, 16, and 32. So the biggest number that can fit into 7 of these is 4. So we're going to do 1, and then 7 minus 4 equals 3. So we're going to go to the next one, and we're going to do 1 minus 2 equals 1, and then this one right here. And we're just going to have a bunch of zeros because this is 8 bits. So that's going to represent 7. And then we're just going to do a similar process for 30. We're going to do 1, 2, 4, 8, 16, and then 32. Okay, so the biggest number out of these that can fit into 30 is going to be 16. So we're going to start right there. And then 30 minus 16 equals 14. So we're just going to go to the next one. And 8 does fit into 14, so we can do that. Minus 8 equals 6. So 4 fits into 6, so we can do that. Minus 4 equals 2. And 2 fits perfectly into 2, so we can do that. And that pretty much makes up 30. So we can just go ahead and fill in zeros right here. And that's our answer. Right here we have one last question to convert from denary to binary. This is important because this one's going to be 12 bits, okay, which means we have 12 digits right here instead of 8 digits. So let's just go ahead and write out our values right here. So we're going to have 1, 2, 4, 8, 16, 32, 64, 128, 256, and then 512. So this is going to be, just to kind of show you the exponents, this would be like 20, 21, 22, 23, 24, 25, 26, 27, and 28. And this is kind of the biggest number we worked with, 431. So the biggest number of these that can fit into 431 is 256. So we're going to put a 1 right there. And then 431 minus 256 is... I'm just going to go ahead and use a calculator because I'm lazy, but on the exam you're actually going to have to be able to do this in your head. So that's just going to be 176. Okay, so 128 fits into 176, so we're going to put a 1 right here. And we're going to do minus 128 equals, okay, so this one I can definitely do in my head. This one is going to be 46 plus 2, so 48. All right, so 176 minus 128 ends up being 48. So 64 is actually too big for 48, so we need to put a 0 right here. But 32 is big enough, 32 is small enough to fit into 48. So we can put 1 right here, and we're going to subtract 32. That's going to give us 16. And then so that means that we're going to put a 1 right here because 16 matches perfectly with 16. And we're actually just done now. So we're going to do 0, 0, 0, 0. And that's going to be our answer. So I hope this was useful to you. I think definitely the hardest part is converting from denary to binary. And what you just need to remember is to go through that process where you're writing out all of these exponents or all of these numbers, and you're choosing the biggest one that can fit into 431. And then you're just moving to the right from there in this direction. So you're just subtracting that number, getting the remainder, and trying to fill that in using binary digits. Like honestly, this is, if you still have trouble, you may just need it explained to you in a different way. And I'm actually going to include some links to some other videos that cover this process so that you can see it explained to you in a different way that may make more sense. Anyways, that was binary to denary, both just in general of converting numbers and then in a iGCSE context. So I hope that was useful to you. Have a nice day.